The stars, they seem so permanent, even eternal. And yet modern astronomy has showed us that they're not. Now, while they have enormous lifespans compared to humans, we know that they can't last forever. How is that? Well, we've seen that they create their energy by fusing hydrogen into helium in their cores, and at some point, they're simply going to use up that hydrogen. It will all be converted into helium, and then the stars must change. What will happen then? Well, that's the topic of this lecture. We're going to look at the life cycles of stars, sometimes called stellar evolution. Now, we're going to see a significant difference between low-mass stars and high-mass stars. And generally speaking, we'll use our sun as kind of the dividing point. In other words, stars with approximately the mass of our sun or less we'll consider low mass, and somewhat more mass than our sun, higher mass. So let's start out then with the low mass stars. You'll recall that we found that, again, the star is fusing hydrogen into helium, and it would be located on the main sequence of our HR diagram. We know, of course, its lifetime there. The amount of time it can spend on the main sequence depends on its mass. Again, the higher the mass, the shorter the lifetime, and vice versa. So what will happen when the star uses up all the hydrogen in its core? Well, simply put, the star is going to move on our diagram. It's going to move up and to the right on our diagram. This indicates higher luminosity, but lower surface temperature. How is that possible? Well, let's get into a bit of the details here. Consider, again, the core of the star composed of hydrogen fusing into helium. At some point, when it's all been converted to helium, it will no longer have quite as much energy, and gravity will be able to contract that core inwardly somewhat. As it does so, it will get hotter, but consider the material outside the core that was not quite hot enough for fusion. That's hydrogen as well. It now will move inwardly, and it will get hotter, and it will begin to fuse hydrogen into helium. So essentially we have a shell of material around the core that is now fusing hydrogen into helium. Well, this shell is generating extra energy for the star. That extra energy is going to be able to counteract gravity and push the outer layers of the star outward. Think of it as essentially increased luminosity of the star, and so again, it will move upwards on our HR diagram. Well, as the star begins to swell and expand, the outer layers are getting farther from the center, and they are going to have a much larger surface area. And as a result, their temperature will drop. And again, we said that that means it will be moving on our HR diagram. So essentially our star moves up and to the right on the HR diagram, as we're going to see now in more detail, towards becoming a red giant. Well, a little more time goes on, and that core again continues to contract, and essentially it's getting hotter and hotter and hotter. That shell of hydrogen fusion is generating helium. That helium, being somewhat denser, is going to migrate towards the center and be added to our core, increasing its mass. So again, with more mass, more gravity, the core will shrink and get hotter. At some point, the core will become so hot, it will be able to fuse helium. What temperature would that be? The extraordinary temperature of 100 million degrees Kelvin. At this point, the star undergoes yet another increase in luminosity. We call this the helium flash. The star now is fusing helium in its core, hydrogen in a shell. It essentially has two sources of energy, and so again, it has a much higher luminosity than it did on the main sequence. On the outside, however, our star will appear to shrink somewhat, and as a result, the surface temperature will actually increase just a little bit, and our star now will move on the HR diagram to the left. So after this helium flash, our star again is going to move somewhat down and somewhat to the left. We will then find the stars are at a relatively stable state for a period of time, not nearly as long as their main sequence phase, but here we call them a helium-burning star, and they would be found on a horizontal branch on our HR diagram. Essentially, they have higher luminosity than a main sequence star of the same surface temperature, but the point being, that means they would have to be larger in size. Well, what will happen when the helium fusion ends in the core, when it's all converted to carbon? Once again, there won't be quite as much energy produced. That core will shrink again. This time outside of our core, we have that shell of helium. It's going to fall inwardly, and helium fusion will ignite there. Outside of that particular shell, we will still have essentially fresh or unburned hydrogen fall inwardly and create a hydrogen burning shell. We now have two shells, or a double shell burning star with a core made out of carbon. So our star has yet again generated additional energy. It will again move up and to the right on our HR diagram for a second stage as a red giant. Now, unfortunately for the star, this is not a stable state for it. It will begin to oscillate. It will not be able to find an equilibrium, and it will expand and contract and expand and contract over time. And over time, these will become stronger, these oscillations. Call these thermal pulses. At some point, the star will essentially pulse so strongly that it will expel its outer layers from the star. That material will drift outwardly. What's left of our star? Well, really just a very small, very hot core. So this material drifting outwardly is now irradiated by very high energy light from that very hot core, and this material begins to glow. And you and I here on Earth might take a picture of that. It's a very beautiful object called a planetary nebula. Really has nothing to do with planets. These objects just appear somewhat round, and so early observers liken them to planets. Again, picture a very small, hot core of the star that's now exposed, and its ultraviolet radiation is lighting up this cloud. This is a fairly brief stage in the star's life, but the point is, as this cloud is gradually expanding, you and I might see a beautiful planetary nebula. Can our star produce any additional energy through fusion? Not for low-mass stars. They simply don't have enough mass and therefore enough gravity to compress the core and get it hot enough to fuse carbon into another element. And over time, that gas of that planetary nebula will gradually expand and disperse back out into space. What we have left then is simply the core, which we now call a white dwarf star. So you can see a very interesting change has occurred to our low-mass star here. We can summarize that on our HR diagram by, again, seeing the star move up and to the right, experiencing that helium flash, burning helium in its core for some time on the horizontal branch, and then reigniting again and becoming a red giant a second time before it expels its outer layers as a planetary nebula, resulting in a white dwarf remnant. So this is how most stars end their lives. Low-mass stars, being the majority, go through these stages and then end up as white dwarfs. So we can summarize those stages. Again, the main sequence, hydrogen to helium fusion in the core. The red giant stage is when we have hydrogen to helium fusion in a shell, and we have this helium core fusing to carbon. Essentially, at some point, we saw a double shell burning star, and then eventually those outer layers are expelled, exposing our white dwarf. So we can really see, again, a tremendous change here in the stars over time. And so giant stars can be much larger than main sequence stars. But now let's turn our attention to high mass stars. We're going to see some similar stages, but some differences as well. Once again, we know that high mass stars will spend the main sequence phase burning hydrogen into helium in their core. And once again, their lifetime on the main sequence phase will depend on their mass. But remember, we saw that high mass stars use their fuel much more quickly in order to generate enough energy to balance their gravity. And thus they're going to leave the main sequence more quickly. Now these will become supergiant stars. So let's talk about the different stages they'll go through after the main sequence. When their cores contract, and they ignite a hydrogen shell, these stars expand even more than the low-mass stars, and we have a supergiant star at the very top of our HR diagram. Once helium core fusion ignites, again, the star may increase its luminosity, but what we're going to see now is that the high-mass stars are able to go beyond helium fusion. They do have enough mass, they do have enough gravity to continue to contract that core more so and ignite heavier elements to fuse. So we're going to see a very interesting scenario play out here now. Again, it comes back to that mass, that stronger gravity, compressing their cores even more, raising them to a higher temperature, and that higher temperature is what's going to enable the fusion of heavier elements. So after the helium to carbon fusion, carbon will be able to fuse into heavier elements as well. This is again higher luminosity being poured out of the star. This is again why the high mass stars have a shorter lifetime. Now as that temperature increases in the core of our high mass stars, you can well imagine that the fusion rate must increase. And our star is furiously generating more and more energy with each successive element being fused. So hydrogen to helium fusion may last for some millions of years in a high mass star, but as we move to heavier elements, helium to carbon may only last for a few million or even less in the highest mass stars. And as we go past carbon, that extreme temperature will cause the fusion reactions to occur even faster, less than a million years, perhaps only a few 100,000 years. And as we work to the very heaviest elements, we'll see those phases can go very, very quickly. So picture then our high mass star, again as it fuses elements in its core, uses them up, the core contracts further, the first shell beyond the core sinks inwardly, becomes hot enough to fuse, the next shell outside of that shell sinks inwardly and becomes hot enough to fuse, and the next shell outside of that sinks inwardly and begins to fuse. So we essentially have a series of multiple shells all fusing multiple different elements. Many of these elements you and I are familiar with. We've seen, of course, how hydrogen can turn to helium, helium to carbon, but for example, carbon can turn into oxygen, oxygen into neon, neon into magnesium, and even heavier elements than that in the most massive stars. Elements such as silicon and sulfur and calcium, all the way to iron, a very heavy, very dense element. So again, picture our star here with all these various shells furiously pouring out energy, occasionally a bit more, occasionally a bit less as each shell ignites. But at some point we have all these various shells. We still, of course, have a vast amount of unburned hydrogen outside of the shells. But ultimately, the star is going to create an iron core. This is a problem for our star. Why is that? Well, iron is a very dense, heavy element, and in order to try to fuse it together, not only do you need to have an extraordinary temperature, but you simply don't get enough energy out of the reaction. Well, if our core is trying to fuse iron and can't get enough energy to support itself, you know what's going to happen. It will contract inwardly, and surely all the shells around it will also contract inwardly. But here is where the star is going to meet its demise. If iron cannot fuse, there's nothing to stop the gravity from compressing it catastrophically. So essentially we would say our iron core is going to collapse inwardly under the enormous gravity of this high mass star. All those shells will collapse catastrophically. All of that material on the outside of them will collapse inwardly. And so we have what we call a core collapse. Now the temperatures and pressures literally become astronomical. Normal matter, of course, we know has nucleus and electrons orbiting around these. Well, these electrons are forced into the nucleus. There they will combine with protons to create neutrons. Well, as we compress this core, collapse this core, these neutrons begin to bump together. There's no empty space anymore in any atoms. We have an extraordinary density of matter. all this infalling material now is going to run into that extremely dense neutron core. Well, that core is so dense that all of this material rushing inwardly under the pull of gravity now will literally bounce off that extremely dense neutron core, and the star now will explode outwardly in a catastrophic explosion we call a supernova. This is one of the most powerful events we know of in all of nature. The destruction of a high-mass star as its core collapses, all this outermost material falling inward bounces off this extraordinarily dense neutron ball, and we have an explosion called a supernova. Well, that core now we'll actually call a neutron star, and the energy released in this explosion is, again, literally astronomical. Think of it. More energy, far more energy than our sun generates in its entire lifetime is released in a supernova explosion. What an incredible event out in nature. In fact, the energies are so great as this material rushes outward that any remaining matter is greatly compressed as this extraordinarily powerful shock wave sweeps outward for several hours, compressing this so much to such a high temperature that in the shock wave itself, in this regions, we literally can have fusion occur. And that fusion can go beyond iron and create some of the heavier elements that you and I know about. So what an extraordinary event as high-mass stars here explode as supernova. They create the heaviest elements in nature. You can well imagine that all of this material then is spewed out into space in a far more violent manner than even our previous low-mass planetary nebula. And so this material goes back out into space. We saw in a previous lecture that essentially it mixes with the interstellar medium and can then in the future be used for new star formation. What are we left with? Well, usually we're left with a very, very tiny neutron star. This incredible core is squeezed down to a mere few miles across, and yet it would have more mass than our sun. In fact, the density is so high, if we were somehow able to obtain a sample, even just 1 cubic centimeter, about the size of a sugar cube, on Earth it would weigh over 100 million tons. Hard to imagine that type of density. Well, it's only because of that extraordinary density that, again, that inward collapse bounces outward. However, detailed calculations tell us there is one exception to this. If our star begins life as one of the most massive of all stars, perhaps more than 10 to 20 solar masses, as it experiences this entire supernova process, its gravity is so powerful that even the neutrons can be crushed. Hard to imagine that, but in a few rare cases this would take place. What occurs then? Well, this core cannot support itself against gravity and will continue to collapse. How far will it collapse? Well, here's where it gets even harder to understand. It will continue to collapse down to an infinitely small point. Now, the mass can't disappear from our universe. The mass is there, the gravity's there, but our object no longer really has a physical, tangible size. What is this? A black hole. You probably heard the term. And this refers to an extremely massive star undergoing its supernova collapse that literally crushes the neutron star even further. Now we're going to come back and explore not only the white dwarfs we saw, but the neutron stars and black holes in our next lecture. But for now, I think you can see the extraordinary stages that a high-mass star goes through. So let me just summarize those, and then we'll wrap up. Again, after our main sequence stage, we saw that our high-mass star will expand to supergiant size. It will continue to fuse heavier and heavier elements in various shells around the core. As the core continues to collapse, or contract rather, and fuse heavy elements, succeeding shells will fall inwardly and get hot enough to fuse. The next succeeding shell will fall inwardly and get hot enough to fuse, and so on and so forth. At some point, though, we saw that when the core becomes iron, the star simply cannot obtain enough energy from iron fusion. That core will collapse catastrophically. All of the star's mass will now collapse catastrophically inward, and only the extreme pressure of crushing the electrons into protons, only the extreme density of neutrons will normally stop this star, and an outward explosion will occur, a supernova explosion during which even heavier elements than iron can be fused. And so we have this tremendous event in nature. We saw that even in a few extreme cases of the very largest mass stars, even here the neutron density is insufficient to stop the inward collapse, and that object is literally crushed down to essentially zero size and becomes a black hole. Well, it's been quite a story we've seen of high mass and low mass stellar evolution. Let's go ahead and do our review to summarize. In a low mass star, when it fuses hydrogen to helium in its core, we know that's the main sequence stage. Once that core becomes all helium, it will contract. Material outside the core will fall inwardly. This extra luminosity, this extra energy will now expand our star to become a red giant. Eventually, the core will become hot enough to fuse helium into carbon and will, for a time, take up residence, as we said, on that horizontal branch. But at some point, again, that core will contract again, and that first shell will fall inwardly and fuse helium to carbon. A new shell, a second or double shell, will now form and fuse hydrogen to helium. This double shell state is not stable, however, and the star eventually will expel its outer layers as a planetary nebula and leave behind a white dwarf star. How about for our high mass star? Well, again, after hydrogen fusion in the core, that main sequence stage, once again our core made of helium will contract and get hot enough to fuse to carbon. And again, we'll repeat what we just saw. A shell outside of that will fall inwardly and fuse hydrogen to helium. But as this core now contracts, it will go on and fuse carbon into oxygen and successively heavier elements. At each stage, as the core contracts a little bit more, each particular shell will fall inwardly and a new shell will form, and we eventually end up with multiple shells, all generating energy, bloating our star to enormous size as a supergiant. However, we saw there was ultimately a dead end. When the core turns to iron, we saw it cannot any longer support itself. It collapses catastrophically. All of the outside material catastrophically falls inward and bounces off this extremely dense neutron star in a catastrophic supernova explosion. Only in the very most massive stars does gravity overcome even the neutron star pressure and create a black hole. So again, it's an amazing story that modern astronomers have been able to uncover here. We now can look at the stars and not only know about their properties today, currently, as we observe them, but we can begin to put together their life stories. What a fascinating topic we've uncovered here. And we'll continue on and learn more about the fate, again, of white dwarfs, neutron stars, and black holes next time.